Thank you everyone for taking the time to join me on our webinar. Today we will be talking about the Fluid Catalytic Cracker, flue gas, valve automation, and how REXA can improve its performance and efficiency. My name is Manny Vasquez. I am the Oil and Gas Industry Manager for REXA, and I am pleased to have the opportunity to present this webinar to you. For some of you attending, you may have participated in my last webinar, where I spoke about the regenerator and spent catalyst slide valves. So parts of this presentation will be a great refresher to you. As you all know, the FCC is really complex, so I will do my best to summarize the process. To save us a little time, there are some parts of the FCC process that I will purposely leave out for another webinar. And just like last time, I'm confident that you will find this webinar informative and gain some valuable insight. So let's begin. For today's agenda, we will begin with a brief overview of the FCC. As I mentioned before, the FCC is a complicated system, so this time around we will be focusing on the flue gas process. I will lightly touch on other systems of the FCC, such as the regenerator and spent catalyst, the fractionator, and the wet gas compressor. You may remember that the flue gas valves are operated hydraulically, so we will also discuss some of the common problems associated with hydraulic power units. Last, we will discuss the benefits of REXA's electraulic actuators. All this will be followed by a question and answer session at the end of this presentation. The FCC is one of the major conversion units in a refinery. The FCC upgrades low-value, heavy feedstocks into high-value, light products such as gasoline and jet fuel. It produces a significant portion of the refinery's process margin. The FCC process uses a fluidized powdered catalyst to vaporize and break the hydrocarbon liquids and convert them into gasoline and jet fuel. There are several different proprietary designs that have been developed for modern FCC units. Each design is available under a license from its developer, and they each claim to have unique advantages and features. Some of the FCC design developers are CB&I, ExxonMobil Research and Engineering, Shell Global Solutions, Kellogg Brown & Root, and Universal Oil Products, amongst others. There are two different configurations for an FCC unit. There's the stack type and the side-by-side type. This slide shows a stack type design where the reactor and the regenerator are contained in a single vessel. Here you can see the reactor above the catalyst regenerator. This particular design is by Kellogg Brown & Root. This diagram shows a detailed view of the UOP side-by-side FCC design. The regenerator is found on your left, while the reactor is on your right. This is the heart of the FCC process. In this diagram, you can also see the path of travel of the hydrocarbon, the catalyst, and the air. I will use this slide to help explain the FCC process. To begin the process, preheated feedstock oil is introduced at the bottom of the reactor riser, together with hot catalyst and lift gas. The feed and the lift gas are found at the bottom of the reactor to the right of the diagram. The hot catalyst comes from the regenerator. The hot catalyst mixes with and vaporizes the feedstock, and the resultant vapors carry the catalyst upward through the riser. Cracking occurs as the vapors and catalyst travel up the riser. This is a very fast process. The contact time between the hydrocarbon and the catalyst is about 2 to 3 seconds. At the top of each riser, the catalyst oil mixture is quickly separated from the hydrocarbon vapors to minimize further cracking reactions. The bulk of the catalyst separates from the oil vapors at this point and drops into the bottom of the disengager. One thing to keep in mind is that you want to be careful not to overcrack the molecules because it will create lower yielding light ends. So if the contact time between hydrocarbons and the catalyst is longer than 3 seconds, you could overcrack the molecules and end up with methane and ethane, which have a lower yield value than gasoline. Now remember, You want to end up with as much gasoline as possible because this is where you will gain the most value for your process. One more thing to note, FCC catalyst particles are composites of various types of zeolites and various types of active aluminas. Clay filler and silica or alumina soul binder are also part of the mix. In addition, catalyst manufacturers shape the catalyst to maximize its surface area. In the reactor, that is the vessel to your right, the cracked product vapors are separated from the so-called spent catalyst by flowing through a set of two-stage cyclones within the reactor. Remember from our last webinar that spent catalyst is the name given to the catalyst that was used to crack the feedstock oil. The reason it's called spent catalyst is because during the cracking reaction, the catalyst becomes coated with hydrocarbon residue, commonly referred to as catalyst coke. The spent catalyst then flows downward through a steam stripping section, which is a section circled by the red ovals, to remove any hydrocarbon vapors before the spent catalyst returns to the regenerator. I will briefly mention that the flow of spent catalyst to the regenerator is regulated by a slide valve in the spent catalyst line. This valve is known as a spent catalyst slide valve and is outlined in blue circle toward the bottom of the diagram. This was the topic of our last webinar. Following the cracking reaction, the hydrocarbon vapors are routed to the unit's fractionator, and a fractionator is similar to a distillation tower. This distillation process essentially separates the hydrocarbons into the different yield streams, such as naphtha, gasoline, distillate, light cycle oil, also known as LCO, and other heavier hydrocarbons. The vapors that are not converted to liquids are routed to a wet gas compressor, where they are compressed and routed to a high-pressure condenser for further processing. The reason this process stream is called wet gas is because it contains a relatively high portion of hydrocarbons that are recoverable as liquids. Remember in our last webinar that we discussed that the coating known as catalyst coke greatly reduces the reactivity of the catalyst, and so it has to be removed. So, the primary purpose of the regenerator, the vessel on your left, is to remove the coating by burning it off. The regenerator accomplishes this task by introducing air, as shown by the green arrows at the bottom of the regenerator, which burns off the coke coating, essentially rejuvenating the catalyst. Once the catalyst has been rejuvenated, the flow of regenerated catalyst is controlled by the regenerated catalyst slide valves, shown at the bottom of the slide in a blue circle. This valve was also discussed in my previous webinar. Last, I want to mention the topic of today's webinar, and that is the vapors that result from the catalyst coke burn-off, otherwise known as flue gas. So what is flue gas, you ask? Flue gas are the combustion products that exit the regenerator from the burning of the catalyst coke. A typical flue gas stream will contain the following gases: nitrogen, carbon monoxide, carbon dioxide, oxygen, steam, and traces of sulfur dioxide and other nitrogen oxides. Flue gas will also contain catalyst particles. What happens to the flue gas? Well, one of two things happens to the flue gas. It can either be vented to atmosphere, or it can be converted into electrical energy via a power recovery turbo expander, also known as a power recovery train or PRT. Regardless if the flue gas is vented or converted to electrical energy, the flue gas must undergo an air purification process that removes catalyst, fines, and train in the gas stream. Before it leaves the regenerator, it will go through two-stage cyclones to remove and train catalyst. Then, it will go through a flue gas valve where it will be diverted to a third-stage separator for additional catalyst removal. The flue gas then goes through a carbon monoxide boiler or heat exchanger to produce steam. Last, it will make it pass through what is known as an electrostatic precipitator, or an ESP, to remove residual catalyst in order to comply with local environmental policies before being released to the atmosphere. The ESP contains high voltage electrodes that impart a negative charge on the catalyst particles entrained in the flue gas. The negative charged particles are then attracted to ground collecting plates that are positively charged. And as you can see, the catalyst is then deposited on the collecting plates below. The flue gas from the SCC process exiting the regenerator has a high pressure, high temperature and volume, making it a potential source of energy. Using a turbo expander allows this energy to be recovered. There are a few configurations to recover power, and one can opt to couple the expander directly to the main air blower to provide shaft power, or the expander can be coupled to a generator to produce electricity. This diagram shows the expander directly coupled to the main air blower. The good thing about this power recovery is that it is seen as green power generation, since it is taking advantage of combustion gas, and no additional carbon dioxide or sulfur or nitrogen oxides are created with this generation. This can provide carbon offsetting and economic benefits to refiners by selling the extra electricity to the grid. One more thing to note is that the flue gas valve not only helps control the regen and reactor pressure as I previously explained, but it can also serve as a speed controller to the turbine generator during startup. So as you can see, the flue gas valve can serve two purposes. This diagram shows a complete flue gas system with third stage separator, ESP, and turbo expander. The regenerator pressure controller is critical to maintaining the pressure balance in the SCC cracking section, which in turn is critical to maintaining smooth catalyst flow between the regenerator and the reactor. Regenerator pressure must be controlled within very narrow limits, both to control catalyst flow and to avoid lifting and release valves provided on the main air blower discharge and third stage separator outlets. A flue gas valve or bypass valve located in the regenerator flue gas line is used to regulate the regenerator pressure, which in turn is used to control the differential pressure between these two, the reactor and the regenerator. For the purposes of this webinar, we will only discuss the pressure differential controller of the regenerator. The other FCC controllers that you see on this diagram have been discussed in the previous slide valve webinar. They are also very important and make it part of the entire FCC control scheme. Keep in mind that catalyst flows from the reactor to the regenerator against a slight pressure difference between the two vessels. The pressure due to the catalyst head in the reactor standpipe and stripper must be great enough to overcome this differential. Like the regenerator, an increase in reactor level will increase the spent catalyst slide valve differential pressure, while an increase in regenerator pressure will decrease it. The regenerator pressure is directly controlled by a pressure differential controller, as shown inside the red circle, which operates the flue gas valve. This pressure must be adjusted to balance the spent and regenerated catalyst slide valve differential pressures. While steady valve differential pressures are needed to keep the catalyst circulating, the effects that changes in these pressures have on each other are also important. One of the most common types of valves you will see in this type of application is a butterfly valve. Depending on the capacity of the FCC, these butterfly valves can range in size between 30 inches all the way up to 84 inches in diameter. Sometimes you will find two butterfly valves in series, with one valve fully open on standby, while the other valve modulates. You may also find smaller bypass butterfly valves next to the flue gas valve, which will be called into service in the event that there is more flue gas than the PRT can handle. Slide gate valves may also be used in flue gas applications like the one shown here. Here you have two different designs, a hot and cold shell. One of the main differences between these two designs is that the cold shell utilizes an internal suspended cone. And in this case, we also have these double disc flue gas valves. Now, these critical flue gas valves are operated by hydraulic actuators. These hydraulic actuators are powered by what you see in the picture, known as a Hydraulic Power and Control Unit, HPCU. Many of you have seen these HPUs in your refineries, so you may be familiar with them. This particular HPCU controls two valves. You can also see a long cylindrical accumulator to the far right in black. The reservoir tank is buried behind the power boxes, and what you can't see are the pumps, filters, gauges, block and bleed valves, and the rat's nest of hoses and tubing that is coming out of these HPUs. All of these are potential sources of leaks and failure. Many issues with an HPU system often originate from the breakdown of hydraulic fluid. Since these HPUs are an open-loop system, air is allowed into the reservoir. This flaw is inherent to its design, and it pretty much guarantees premature breakdown of hydraulic oil. A lot of these HPUs sit below decks of moving or shaking parts, thus dislodging dirt and debris that will eventually get into the oil reservoirs. If the reservoir isn't cleaned out or if the filters aren't changed frequently, dirt particles could circulate through the hydraulic lines and potentially clog servo and check valves. This would then prevent the valves from doing their function of opening, closing, or holding position. Here's the filter element that came out of an HPU. Look at the large metal particles on the filter. Also note that the filter is swollen, a sign of an old and dirty filter that is probably forgotten and hasn't been changed out in a very long time. On this slide, you can see the myriad of passages, ports, springs, and other moving parts that are less susceptible to dirty oil and particulates. Particulates can become lodged within these parts and prevent the servo valves from doing their function. This can lead to the valves not closing or opening or holding position. Drift is another problem that can occur as a result of dirty servo valves. HPUs are designed to have dozens and dozens of different sized O-rings, which can potentially dry out and become a leak path. Furthermore, block and bleed valves found on the HPUs will eventually wear out and also become a leak path. In addition to checking O-rings and block and bleed valves, you also have to inspect hundreds of feet of hose, tubing, and fittings because they too can become leak paths. Oftentimes, technicians can spend hours and hours tightening or replacing leaky fittings, tubing, and hoses. In this picture, you can see the oil leakage in the back and the white bucket below ready to catch the dripping oil. Unfortunately, and very dangerously, this is the mode of operation for this refinery. For those of you that have worked in refineries, how often does maintenance or operations check on the HPU reservoir level? If this task is not some kind of daily checklist or on a PM schedule, checking reservoir level is often never done until there is a problem. This can be potentially damaging if the HPU is constantly leaking oil. Many FCCs were designed and built over 30 to 40 years ago. Since their installation, the FCC unit may have increased output. Were the HPUs updated to handle the new load and speed requirements? A lot of these HPUs are so old that parts are now obsolete. When I was the FCC instrument engineer in Los Angeles, BASCA was the HPU manufacturer that actuated the slide valves. We had an upcoming turnaround, and BASCA was unable to provide parts because they had none. The parts were now obsolete. Several refineries that I have visited throughout the world have complained about the same problem. Yet, another problem is that HPUs dissipate heat through their reservoirs. Therefore, the system's capacity to dissipate heat must exceed its loads. If the reservoir level is low, or if the HPU has a cooler that is not working properly, the oil temperature may get excessively hot to the point of damaging seal compounds and accelerating oil degradation. With the hundreds of valves, pumps, and other instruments and rotating equipment that must be placed on preventative maintenance programs, do you really want to add another item to that list? I sure don't. HPUs are maintenance intensive. You have to change filters, inspect O-rings, change desiccant, flush and filter the existing oil, add oil, maintain the pumps, inspect the block and bleed valves, tighten loose fittings and hoses, And if everything is okay, you could then move on to the next HPU to repeat the same process. The HPUs that we had to maintain in my FCC had an 82-point inspection plan per HPU. The FCC alone had 7 HPUs, which took about 80 man-hours to complete. And that had to be done twice a year. Last, since the servo valves found inside the HPUs require a continuous circulation of pressurized oil, the pumps and motors have to run 24 hours a day, 7 days a week, 365 days a year. As you guys can see, stocking parts for these HPUs, the man-hours required to maintain them, and having pumps run all day, every day, becomes a very expensive proposition. Any of these problems already mentioned can lead to a number of other problems, such as decreased production due to slow-moving, drifting, or non-responding actuation, decreased inefficiencies due to fluctuations in hydraulic oil temperature, hydraulic pressure, and level, which in turn increases the use of heat, feedstock, air, and catalyst, and can lead to unscheduled shutdown and total loss of production. Many times, engineers fail to think about the total cost of ownership. I know this very well because it happened to me. In my quest to upgrade an existing HPU, I failed to think about the here and now. Instead, I got stuck with extensive PM list and tens of thousands of dollars in extra maintenance costs that I had to justify to the reliability manager. I didn't think all of the maintenance, time, money, and effort that these HPUs required. Maintenance should have been designed out rather than designed in. Consider this. What if oil cleanliness did not have to be monitored? What if the source of oil contamination and breakdown were eliminated by design? What if no hydraulic oil sampling, filter maintenance, or flushing were required? What if I never had to replace another HPU filter in my life? Well, I'm glad you asked. Enter REXA Electraulic Actuation. Let's talk about some of the benefits of the electraulic actuator. To start, it's a very unique design, unlike anything on the market today. This electraulic actuator is a true closed-loop hydraulic system, which is hermetically sealed, thus eliminating the possibility of water, air, dirt, and debris from entering. There are no filters or oil changes to do, making it very maintenance-friendly. How does this happen? Well, first allow me to explain. The electraulic technology consists of 2 primary components. There is the mechanical assembly and the electrical subassembly. The mechanical portion is attached to the slide valve itself. The electrical subassembly is basically the positioner for the actuator. This is where the main power supply and control signal are routed. It is also the origination of the 4 to 20 milliamp signal, which is then connected to your DCS. We separate the electric and mechanical assemblies for ease of access and operation. There are many severe applications, for example, in desert or Arctic environments, where onboard electronics simply would not survive. The control box can be mounted in a convenient location to the valve or up to 700 feet away. Next, let's take a closer look at the REXA hydraulic circuit. This is the real difference with our technology in comparison to HPU-based electrohydraulic systems. The centerpiece of the electraulic circuit is our bidirectional gear pump, which is coupled to the REXA brushless motor. The gear pump works in conjunction with the flow match valve. During operation, when the actuator is at the desired position, spring-loaded ball checks are locked in place to prevent the flow of oil through the flow match valve. But when there's a signal change, the motor activates, turning the bidirectional gear pump, which instantaneously builds pressure, allowing the ball checks to open. The oil is then transferred through the flow match valve from one side of the cylinder to the other. Once the actuator has reached its desired set point, the motor stops and the ball checks are seated, stopping the flow of oil through the system. Now in the standby mode, power draw is only about 50 watts. The cylinders that we use are dual rod, so the oil volume extending on one side of the cylinder is equal to the volume entering the other side. The design eliminates both the requirement for an external reservoir and the need for continuously circulating oil through the system. The displaced fluid then flows into and out of the flow matching valve to each side of the hydraulic cylinder. In this slide, you can see a pictorial representation of the power module and a cutaway view of the power module. As you can see, this is truly a closed-loop system, so there's no breakdown of oil, no filters to change out, no block and bleed valves to maintain, and no pumps to inspect and repair either. So you can go from a traditional HPU with the rat's nest of hoses, conduit, wiring, and all that leaking oil like the picture you see on the left, to a clean REXA installation, virtually eliminating another PM task and effectively reducing your total cost of ownership. That is the picture on the right. REXA completely eliminates the guesswork out of asset management. These are just some of the features of the REXA actuator. 0.1% repeatability, 100% duty cycle, fail-safe options, spring accumulator options, fast actuation speed. Last but equally important, one of the reasons that I came to work for REXA was the excellent field service they provide. When I was the FCC I&E engineer, it was critically important to me that a company stand behind their products 100% and be available whenever I needed them. You guys know how it is whenever you're in shutdown mode and time is of the essence. You need a field service technician quick, and you need him to get ready as soon as he gets there. I am proud to say that we have some of the smartest, most technically savvy, and mechanically inclined technicians in the industry. Should you need any field services, REXA is willing to help with installing, commissioning, modifications, refurbishments, training, and any shutdown and turnaround support. We have a great field service team, and they're ready to go on a moment's notice. In closing, REXA is not a product, but rather a solution that will make a difference for your plant on critical applications such as FCC slide valves. It's a sound engineering decision that will be valuable in your process control and optimization goals. REXA is an investment that will pay dividends. Thank you all again for joining me on this webinar. Please feel free to contact me anytime, and I'll be more than happy to assist you. Or if you prefer, we could arrange a visit to your refinery to see how REXA can be of service to you. My contact information is found below.